All right. So, guys, by way of transition, here's the deal. And this happens very infrequently, but every couple years, somebody comes up to me either during or after grading this, right? Grading this homework assignment. And I don't know, I would have never picked up on this, but some people do very infrequently. But they look at this homework, and guys, I mean, look at it from a distance. It's like, holy smack, that's a lot of stuff, right? And every now and then, I'll have a student that'll come up to me and they'll be like, aren't a lot of these reactions kind of the same, only they have different chemicals? And I'm like, oh shoot, you're way smarter than me. But guys, the answer is yes. And I won't ask you to do this, but if you were to do this, and if you were to go back and actually read through these maybe a little carefully, not by trying to balance them, the work's already done, you'd start to look at these and you'd be like, yeah, there are some patterns here. Well, guys, it turns out that's not coincidence. It turns out that every one of the reactions that's up here on my wall in your homework, guys, every one of these reactions can actually be classified as one of 5 reaction types. So guys, what we're going to do today is we are actually going to talk about these 5 types of reactions. We're not going to go back and redo these, but guys, what you're going to see is that these reactions all fit into 5 general categories. So you're going to learn these general categories. And then what's going to happen is after you've learned the categories, we're going to go into lab on Tuesday and we're going to do all of these reactions. It's actually really a fun day. But guys, today what we're going to do is we're going to talk about the patterns. We're going to talk about these types of reactions. So guys, I'll tell you when to start writing stuff down. But guys, basically what we're going to do is this. So remember this from your notes last time, and we talked about the idea that we can balance equations using coefficients. That was part A to your homework. And then parts B and C was write their chemical formulas by balancing charges, and then balance the equation. And guys, now what we're going to do next time is now today. Guys, today what you're going to learn to do is identify reactants and products. How do you know? Because there's patterns to these reactions. And so guys, today what we're going to do is we are going to learn these patterns. Now guys, please do not write this down. This is not for today, but I want to share this with you now. So guys, we know the chemical equations are used to represent reactions. We know how to balance them. So guys, what we're going to do today is we're going to talk about these 5 general types of reactions. But guys, these are them. Do not write them down. But this is basically our to-do list for the day. In a moment, you're going to title your notes single displacement, and we're going to talk about what that is. Then double, synthesis, decomposition, and combustion. But guys, as we do, this is going to be the redundant pattern. Again, you don't need to write this down. So guys, what's going to happen in just a moment, follow the laser, we're going to talk about single displacement reactions. I'm going to define it. I'm going to give you a general form. Then I'm going to give you a rule of thumb that makes your life a lot easier. Then we're going to look at an example. When we're done with that, we're going to do that for double displacement and on and on. So this is going to become super repetitious. Get the idea? But again, guys, the connection is this. These examples that I'm going to give you at the end of each one of these are then the reactions that we're going to go do in lab on Tuesday. Get the idea? Okay. Now, guys, one other thing, again, please don't write this down, but this will be important for the lab. I'll remind you after spring break. Guys, when we write balanced equations, when we do them in lab, we have to include subscripts. And these subscripts indicate the phase of the reactants and products. Now, you already know solid, liquid, and gas, right? So we're going to abbreviate. Solid is an S, a liquid is an L, and a G is a gas. But there's one other phase that you need to know, and it's aqueous. Because what's the root word for aqueous? Aqua, water. That simply means dissolved in water. We'll talk about this more on Tuesday, but I wanted to lay it in front of you now. You guys ready to go? Here we go. So guys, single displacement reactions. Single displacement reactions, and this is where you do start taking notes, are a single exchanging of partners. So in order to understand this, guys, you need to understand the word displace. So when you're ready, join me up here, and I'm going to show you what displacement is and isn't. So ready? Follow the coffee cup. You see it? Still see it, right? That's not displacement. Displacement does not mean to move. Guys, watch the subtle difference. I am now going to displace the coffee cup. What's the difference? Something took its place. Guys, that's what displacement means, is something takes the place of something else. And in a single displacement reaction, guess how many times that happens? Once. It's single. So, guys, then we need to talk about the general form of this reaction. So guys, what a general form is it's literally a hypothetical. There is no element A, B is boron, but that's not this, and C is carbon, and that's not carbon. This is generic. Write it down with me. So A, which has a positive charge, is going to react with BC. And guys, BC is a compound. Think NaCl, think H2O, think CO2. It's a compound that's made of two elements. So guys, the question then becomes this. What's going to happen when positive A reacts with BC? Well, we've got to remember something. Guys, remember when we write chemical formulas that the positive guy is first and the negative guy is second, right? It's NaCl, not ClNa. So guys, think through this. If B is positive and C is negative, which one will positive A hook up with? Negative C, right? It's not going to hook up with B because like charges repel. And so guys, A is going to hook up with C, and that's going to form AC. Now guys, the question is then this. What happens to B? Well, B goes home alone. Do you see the displacement? Who got displaced? B. See, B was chilling with C. And A, I mean, this is kind of like what happens at date dances, right? You got Sally and Jim dancing together, and Larry comes over and goes, hey, can I dance with Sally? Who just got kicked out of the couple? Jim. Same thing's going on here. You've got B and C hanging out dancing together, and A comes in and goes, hey, yo, can I hook up with C? And B stupidly says, okay, and B goes home alone, and A ends up with C. Get the idea? That's the displacement. But guys, if you understand that, then you should also understand how to figure this out. What if A is negative? Go ahead, Matt, say it again. Good for you. If A is negative, it's going to hook up with B, but guys, go slow. I'm going to do it wrong. Please don't do it with me. So guys, do you see what Matt sees? That this is still positive and this is still negative. So now negative A is going to hook up with B. But guys, talk to me about this. Why is that wrong? Which one always goes first? Positive one. So guys, this is wrong because B is positive. So your product would actually be B, A, and then C gets the bootski. Is that okay? You feeling okay about that? So guys, we've got the definition, we've got the general form. Now what I love to call the rule. Oh, I hate my board. Guys, this is going to freak out. Hold on. All right. The rule of thumb. So guys, if you're not familiar with the concept, a rule of thumb is just a general thing to remember to help you do this right. So guys, the rule of thumb in this example is this. if you have an element like A reacting with a compound like BC, that will always be a single displacement reaction. I was going to have you go through and find all the examples in your homework, but we're not going to do that. Your previous homework. But guys, what we need to do now is we need to look at an example. And this is our example. Write it down with me big. And we're going to play with this. Josh, while we do this, keep your diatomic spidey senses sharp. All right, so guys, how do we know that this is a single displacement reaction? Well, over here on the left, we got an element zinc, right? Again, you're going to do this. This one's fun. You're going to do this in lab on Tuesday, and then you're going to blow it up. We'll talk later. But guys, so this, actually, it's really fun. So this is zinc, and this is hydrochloric acid, HCl. So guys, this is a single displacement reaction. But in order to figure out the products, just like in our general forms, we need charges. I'm going to save you the pain of doing this. So guys, looking at the periodic table, you're going to find out that zinc is +2, hydrogen's +1, and chlorine is -1. I'd strongly encourage you to do this with me. So guys, who's zinc going to hook up with? Positive hydrogen or negative chlorine? Negative chlorine, right? But now we've got to be careful, because if zinc is +2 and chlorine's -1, how many zincs do we need? Chlorines? 2. So guys, the product is going to be ZnCl2. Does the equation balance? No. But we'll figure that out in a minute. So now, Josh, I don't mean to call you out, but let's do this. Hydrogen gets displaced. So as I was speaking with Josh about earlier, when you write that, you should get twitchy. You should be like, well, hydrogen doesn't hang out by itself, and hydrogen's got no one else to hook up with, so what does hydrogen do? Bonds to another hydrogen. This is H2. So actually the dance analogy isn't that bad, because the guy that got displaced actually just hangs out with his buddies. See? Life lessons. All right. So guys, now we've we've written the equation. Now we need to balance it. And this is just like the olden days. So we've got 1 zinc, 1 hydrogen, 2 hydrogens. So we need a 2. And then we've got 2 chlorines and 2 chlorines, and this is balanced. And we do a little chemistry dance, and we're all done. You guys good? Questions on that? So guys, I would propose this. If you understand single displacement, you also understand, this is driving me batty, guys, if you understand single displacement, I would suggest to you that you also understand double displacement. Only how many times is it going to happen now? Twice. So guys, double displacement is a double exchanging of partners. Now guys, some of you are about to have a really interesting aha moment. So guys, as we're starting to talk about double displacement reactions, don't be passive. Because if you're engaged in this, you're going to go, But make sure, and if you don't see it, it's fine. We'll talk about it. But guys, let's talk about the general form. And the general form is this. We've got A, B, a compound. And AB is hooking up with CD. Again, guys, don't be passive. So what do we need to know to figure out who hooks up with who? Charges. So we know that A is positive, we know that B is negative, we know C is positive, we know D is negative. So Matt has been on this right from the start. I think a lot of you see it, but let's talk. So guys, if A is positive, is it going to hook up with positive C or negative D? Negative D. So we're going to have an A and we're going to have a D. Now guys, if B is negative, does it hook up with C or D? Well, D is already done. He's already gone somewhere. So B is going to hook up with C. Yeah, B is going to hook up with C, right? But why do we not write down BC? Positive first. So we're going to go C, B, and that's our double exchanging of partners. So now guys, please do not write any of this down, but watch what's happening. Positive A is hooking up with negative D, and positive C is hooking up with negative B. So guys, they're literally, listen carefully, they're literally trading partners. Sound familiar? When previously in the year did we experience something where things traded partners? Do you remember? The precipitation lab, right? We had the positive and the negative from one, the positive and the negative from other. And when we wrote this down on all of these lines, we were taking the positive to the other negative and the negative to the other positive. Guys, every single reaction that you did in that precipitation lab, they were all double displacement reactions. I just couldn't call it that because you didn't know what it meant. But guys, every single reaction that you did in the precipitation lab was double displacement. So let's then talk about I'm serious. Oh, remember how computers were supposed to make life easier? So guys, let's talk about the rule of thumb. And it's literally just this. Compounds go in, compounds come out. So, and I'll slow down. But guys, let's talk about an example. Ki, a compound, plus lead 2 nitrate, a compound. Now guys, here's the sad bit. This is actually a really cool reaction. It's actually a precipitation reaction as well, but it makes this amazingly vibrant yellow precipitate. And I used to do this in beakers with my class when I showed them this reaction, but now it's illegal for me to do because I can't dispose of the lead. Lead is actually a neurotoxin, and after what went down in Flint, Michigan, we are really twitchy about lead here in the U.S., and so we're not going to... You guys know about what happened in Flint, right? Do you know? I'll keep it short, but the bottom line is this. Flint, Michigan, their infrastructure that brings the pipes that bring water to their homes are almost 100 years old. And they're actually made of lead. That's where the name plumber comes from, because the Latin for lead is plumbus, and if you worked with plumbus, you were a plumber. And it used to be that all of our pipes were made of lead. And then we found out that lead's a neurotoxin, so we took it out of paint, we took it out of gas. But they didn't replace the lead pipes in Flint, Michigan. But it wasn't a problem because over the decades, those pipes had become so encrusted with minerals that the water actually wasn't touching the lead. It was flowing through the pipes that were coated with these minerals. Well, what happened is about this is almost 10 years ago now, they changed the water source for the entire city. And instead of pulling water out of the Flint River, they started to pull water out of another river. And it turns out that the water from that other river was acidic enough that it ate through the crust inside these pipes. And now all of a sudden the water was flowing through lead. And there was like toxic levels of lead in the water in Flint. And government officials in Flint knew about it and didn't tell anybody. And so for years and years and years, for example, there were moms of little babies making their baby formula out of water that had toxic levels of lead in it. The scary part is that lead is a neurotoxin, but it doesn't show its effects for years. And so even now they're just waiting to see if these little babies grow up with brain defects. And it's all because these government officials didn't want to tell anybody because they didn't want to pay to replace the pipes. Guys, look it up. It was disgusting. Anyway, we're really careful about lead. Yeah. Say that again. Yeah, you'll do a double displacement reaction in the lab, only it doesn't involve lead and it's not going to be yellow. Yeah, you'll see. All right, so guys, double displacement reaction, right? I'm going to save you the problems. Let's do charges. Off the periodic table, potassium's +1, iodine is -1, lead is +2, and as Bree was reminding us a few minutes ago, nitrate's -1. That whole NO3 is -1. So now, guys, let's do the rearranging. Does positive potassium hook up with positive lead or negative nitrate? Negative nitrate, but watch. +1, -1, we need one of each. So that's KNO3. So now you're going, wait a minute, that's not balanced. Not supposed to be. We're writing the formulas first. And then, guys, lead is +2 and iodine is -1. So if we've got +2 lead and -1 iodine, how many leads do we need? 1. Iodines? 2. So our other product is PbI2, and that's the precipitate and the stuff that I can no longer dispose of because it's scary and illegal. Yeah? No, and that's the point. What we've got to do now is balance the equation. So 1K, 1K, 1I, 2 I's, so that means we've got to put a 2 here. Then that gives us 2 K's, so now we've got to sneak a 2 in there. Then we go and continue 1 lead, 1 lead, but I mean, here's the magic. 2 NO3s, 2 NO3s, and it's balanced. And that's not coincidence. All of these reactions balance simply because of the chemistry that's behind it. So we don't get rid of it. We actually add another one over here by getting another KNO3. You okay? Guys, questions there? Okay, this is about to pick up the pace a little bit. Now that we're settling into this idea and these patterns, guys, the last 3 that we're going to do go relatively quickly. You ready? I've learned not to even try to click. Just give up and do this. All right, so guys, the next reaction that we're going to talk about is a synthesis reaction. And when you think of synthesis, you think of synthetic, which means man-made. It's not really what this means. But guys, synthesis simply means this. It's a reaction that makes one product. So lots of things can go in, but only one thing comes out. So, the general form of this reaction starts with AB. But guys, AB, when they come together to make one product, you want to hazard a guess what the product is? AB. It's really just that. Guys, synthesis reactions synthesis reactions literally just stick the bits together. Can I go back to clicking now? Why does it let me do that sometimes? So guys, the rule of thumb then is that this makes one product. So guys, let me show you an example. Yeah, Cal. That's a great question, and the answer is they won't stick. Yeah, if they're both positive or both negative, they repel and there's no reaction. Yeah, that's a great question. All right, so guys, an example is this. What do you get when hydrogen and oxygen bond together? Hydrogen and oxygen, you get water. So guys, the product of this reaction is water. And if you think this is kind of silly, guys, do you know that there are people, actually one guy came back, do you guys know about this? We actually got an astronaut back from the space station yesterday, And you guys know that that was a miracle because the United States no longer has rockets that will make it to the space station. So this astronaut had to come back on a Russian rocket. And we were thinking that Putin might just strand him up there because Russia doesn't like us right now. You guys know about this. But we actually got him back. He was up there 10 days, less than a full year. He was up there 355 days. But anyway, with all of that said, guys, this is actually, I don't know if you know this is where astronauts get the water to drink. Did you guys know that? They don't haul water with them up into space. They actually haul canisters of oxygen and canisters of hydrogen, and they make their own water up in the space station. So the question is why? And the answer is this. Guys, it's not because of weight. The hydrogen and oxygen that go into weight to make the water weighs exactly the same as the water. Law of conservation of mass, right? It's not because of the weight. The reason is this. When hydrogen and oxygen react together to form water, it gives off a bunch of energy. And they actually capture that energy and they use it to make electricity. And when they use that energy to make electricity, it means they don't have to bring anything else into space to make electricity. So they bring hydrogen and oxygen, react it together, they drink the water and then use the energy to drive all the electronics and stuff up in the space station. So guys, again, this is a synthesis reaction, but you do need to know that this reaction also makes energy. Now guys, there's a name for that, and you need to know this. The name is exothermic. Exo like exoskeleton, skeleton on the outside. Exo means out. And so exothermic is energy. Exothermic means energy is being released or going out. Yeah. And NASA uses hydrogen and oxygen to make water. Yeah, isn't that weird? Yeah, it's funny. You guys remember when we talked about that Monday? That they capture the fumes, not the fumes, the vapor that comes off of the Humvees and they drink it? I actually looked it up and it's amazing. For every gallon of diesel fuel that they consume, they get a gallon of water. Isn't that crazy? I mean, it's a lot of water. I didn't know that. It's really kind of cool. All right, so you guys good on exothermic? Yeah? Yeah, and that's the last. Matt, you're so on this. We're not quite done. We need to balance this thing. So we've got two hydrogens, two oxygens, one oxygen. So we need a 2 there, which then forces a 2 there, and now it's balanced. Is that okay? Okay. So guys, you good on synthesis? Then let me show you the next reaction. Synthesis puts things together, right? What name do we give to processes that break things apart? Like trees in the forest and the mold and stuff grows on there. And what happens to that tree? It decomposes. Guys, that is our next... Now it doesn't work again. You guys need to help me figure out this pattern because I don't understand why sometimes it doesn't work. Guys, that's this. If synthesis puts stuff together, decomposition breaks it apart. Get a what? Well, frankly, Kyson, that's what this is. See, yeah, but the problem is that's the problem in the first place. That my computer's hooked up to 4 mice. I don't know if you know this. So 1 is this. I can move that. 2 is this. 3 is the trackpad on my laptop. And then 4 is the screen. And that's actually the problem. Too many inputs. Yeah, it's kind of my life story. So, guys, decomposition then is a reaction that breaks apart a single reactant. If synthesis puts it together, decomposition breaks it apart. So you ready? Radical idea, general form, AB breaks into A and B. Now guys, here's the thing with decomposition reactions. For those of you that are coming back for AP next year, we talk about the patterns that help us understand what things break into. But guys, in this class, you are not going to learn enough chemistry to be able to predict the products. As a result, I will always give them to you. And we'll talk more about that in a minute. But guys, the rule of thumb then is this. You've got one reactant. So guys, obviously I know you know what's next. We're going to look at an example. But guys, please do not write down the example until I tell you to. So we understand, right, that synthesis and decomposition are opposites. Synthesis together, decomposition apart. Check this out. Don't write it down, but here's the deal. We've got hydrogen and oxygen reacting together to make water and energy. What kind of reaction is that? Synthesis. But guys, don't look away. Watch this. So guys, if this is a synthesis reaction, now it's decomposition. They're literally opposites of each other. Now you can write this down. I'm proud to say that I didn't need Miss Call to help me figure out how to make that animation happen. Felt pretty good about that one. You guys good? Okay, now do this. Is energy going in or coming out if it's a reactant? It's going in. And that's not exothermic. That is endothermic. Endo means in. But guys, this is where this gets a little bit interesting, at least to me. So we talked previously about the idea that the astronauts drink the water, but they use the energy to create electricity, right? Well, it turns out that when hydrogen and oxygen react to make water, it can happen in one of two ways. In lab, you are going to do this and you're going to let the energy come out as an explosion. It's actually really fun. So you're going to take hydrogen gas and you're going to react it with oxygen gas and it's going to blow up. And the energy goes out as flame and fire and noise, and it's kind of fun. But guys, it doesn't have to happen that way. The energy can also come out as electricity if we do the reaction a little differently, and then it's useful to the astronauts. Yeah. I love that you know that, Josh. Yeah, I wanted to share the quote when he talked about how he was going to do it, but he cusses and I can't. But that's exactly what they did in the movie The Martian with Matt Damon. Yeah, it's and they're actually talking. So right now we're on Mars, right? We've got the rovers running around on Mars. And one of those rovers, it's really fascinating, one of those rovers is actually up there right now. And there's not much oxygen in the atmosphere of Mars, but there's a lot of carbon dioxide. And so the last rover that we sent up there has this little canister in it where what they're doing is it sucks in carbon dioxide, spits out the carbon, and then traps the oxygen. Because what we're thinking is that if we're going to go to Mars, why take oxygen with us if we can get it out of the carbon dioxide that's already on Mars, and then all we have to take is hydrogen. And so they're thinking that if this works, they're going to send a really big one of those up there and just let it sit for years and just collect oxygen. So when we're smart enough to send people there, they're going to arrive with a bunch of oxygen that they can breathe and turn into water. Yeah, isn't that cool? But yeah, that's exactly what happened in The Martian. So, guys, the idea is this. We know that if we burn hydrogen and oxygen, it gives off energy. It could be heat and explosion, or it could be electricity. That's what the folks do on the space station. But guys, here's the trick. Question for you. When we break water apart, can this energy be heat? Can it be fire? No, what happens if we add fire like a Bunsen burner to a beaker of water? What's it do? It boils. And when it boils, the water molecules come out. The water molecules do not break into hydrogen and oxygen. So how do we get them to break into hydrogen and oxygen? You actually have to add electricity. And guys, it looks like this. So guys, this, I actually used to have one of these. And then one of my AP students broke it. But the way that it works is you add water to the center column, and that water fills, you'll see they're connected at the bottom, the water fills these two side columns. And down here at the bottom, you'll see that they're all connected. But then guys, coming in these side tubes are two electrodes, and they're hooked to kind of a ridiculously strong battery. And watch what happens.
If we connect an electrolyzer filled with distilled water.
So guys, what they've done is they've hooked this up to a battery. And notice what's happening. I think you can see this even from a distance. Abby, do you need to go? Okay. Just watch the last 10 minutes of the screencast. Okay. So guys, notice we've got bubbles over here, and notice we've got bubbles over there. What are those bubbles? Hydrogen and oxygen. We're breaking the water apart into hydrogen and oxygen. Now guys, here's the question. Do you notice how many bubbles there are over here compared to how many bubbles there are over here? You want to guess how many more bubbles are over here? Twice as much. Why? Because water's H2O. So when water breaks apart, we get twice as much hydrogen as we do oxygen, because literally water is H2O. All right, we'll give you a little bit of it. So there's the hydrogen side, there's the oxygen side, and literally it's twice as much. You actually see that in the tube, that this amount is twice as much as that amount, because this is our hydrogen side and that's our oxygen side. Why is that true? It's because the battery down at the bottom, this is the negative side, so the positive hydrogen is attracted, and this is the positive side. Yeah, and that's the positive side, so the negative oxygen's attracted to that side. Huh? It's just like chemistry. You guys good on decomposition? Can we do one more together and then do some homework? Okay, so guys, the last one we need to do is this. Hoping against hope. Nope. Guys, the last one we need to do. Boom, 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 boom is combustion. Yes, wait. Yeah, we are going to do combustion and wait, yeah, we are. We had a little meltdown about 4 years ago when we used to do this really elaborate combustion reaction, and then it set off the smoke alarms and we had to evacuate the school. Well, and it was actually bad enough that the fire department actually showed up in their turnouts and their respirators and crashed my lab. It was not one of my better days. All right, so guys, combustion is the burning of a hydrocarbon. The general form is this. Just write it down. Guys, the reason that you're just writing this down is because there is no prediction. There's no balancing of charges. You're just going to write them down. So guys, a hydrocarbon, hydrogen, not hydrate, but hydrogen. It's carbon and hydrogen bonded together. You guys all know from your Boy Scouting days that if you want something to burn, there has to be oxygen. And then guys, the products are simply carbon dioxide and water. This is the reaction that I balanced for you Wednesday with the propane. Remember we talked about barbecue grill? That was one of those. So guys, let me give, this is kind of worthless, but pretend. The rule of thumb is simply just the general reaction. You've got a hydrocarbon and oxygen always forming carbon dioxide and water. While you're writing that down, does everybody have a copy of the homework packet? You need one? That means I need to find them. Aha. No. Yep. Wait. No. Yes. Anybody else? Yes. Joe, you said yes. And Ellie, you're good, right? Okay. Yep. All right. So guys, with that said, let me show you an example. This. You guys all caught up? I don't want to run ahead of you. You're good? So questions. How do we know this is a combustion reaction? And the answer is two things. Do you see that this is a hydrocarbon, hydrogen carbon? Yeah? Okay. And then guys, we've got oxygen. So now what we need to do is figure out the products. Here's the deal, guys. This is easy. Don't think. If you think, you're going to get this wrong. Don't think, just write. It doesn't matter what the charges are. This isn't single displacement. Guys, the products are always stinking the same exact thing. Carbon dioxide and water. Again, that's the water that the Marines drink. It's carbon dioxide and water. Now, guys, we've got to balance it. We've got 1 carbon, 4 hydrogens, so we needed 2 there. And then that gives us 2 plus 2 oxygens, so we needed 2 there. So now, guys, let me let you in on a secret. Every single one of you in this room has seen this reaction in action. How do I know? Because, guys, CH4 is natural gas. This is the it's called methane. It's natural gas. Guys, this is the reaction that happens every time you light your Bunsen burners. We're done. So, guys, let's do some homework. Guys, grab your homework packets. Keep your notes in front of you. And let's do this. Now I need a copy of the homework. So guys, turning to homework assignment number 2, pen in hand, pencil in hand. Look at page 1. It says categories of reactions. Notice we've got abbreviations, SD, single, DD, double, and so on. Guys, here we go. Let's do number 1 together. Thinking about the rules of thumb, what makes number 1 stand out? It has 1 reactant, which makes it what? Decomposition. Write it down. DEC. Number 2, ready? Compound, 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 compound. What's that? Double displacement. Write it down. Guys, what makes number 3 unique? 1 product synthesis. See how those rules of thumb are really nice? Guys, number 4. Compound, 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 compound. What do you got? Double displacement. Write it down. Number 5, be careful. Element. Element, compound, compound, element. Single displacement. And then, guys, you're just going to keep going. Let me tell you right now, I did write this, and I have no idea why, but I didn't put any combustion reactions in here. My bad. Guys, none of these are combustion. You can just cross it off the list at the top. And that was just my oversight. So now, guys, flip it over on the back. This is where these get interesting. So, guys, we are going to do number 1 together. Please do this slowly and carefully with me so that you can develop a pattern. Now, guys, in order to do this, you'll notice that you are given almost no useful information. This is even less information than you had when you did these at the bottom of today's homework. All that it tells you are the reactants, and that's it. Here's your strategy. Ready? Number one, write the formulas for the reactants. I'll do that with you. So guys, aluminum is +3. Sulfate off the yellow chart is SO4 -2. Where do 3 and 2 meet? Where do 3 and 2 meet? 6. So how many +3s do we need? 2. So we've got Al2. I would encourage you to just write these down below. And then guys, we need how many SO4s? 3. And that goes in parentheses. So there's one reactant. Guys, if you need a refresher on writing chemical formulas, there's a screencast. Come talk to me. Got to be able to write chemical formulas. Now, calcium is Ca, it's +2. Phosphate is PO4, and it's -3. So guys, again, 2 and 3 meet at 6, right? So how many positive 2CAs do we need? 3. You know what? I'm realizing I'm going to run out of space. Let me move this over a little. Okay, so we need 3 calciums. How many PO4s do we need? 2. Oh, in parentheses. All right. So now, guys, at this point, it's now time to think of the rules of thumb. This, please. Thanks. This would have never balanced. All right. So guys, now what we've got to do is we've got to figure out what kind of reaction this is. Make a mental list. Ready? Let's do them in the order that you learned them. Could this be a single displacement reaction? No, because it's not an element in a compound. Could it be double displacement? 2 compounds in. Guys, be careful here. Could it be synthesis? Could be, but we would have to shove all of these things together, and that's not very likely. Could it be decomposition? No, because it's got more than one reactant. Can it be combustion? No, there's no hydrocarbon and there's no oxygen. So guys, it's either double displacement or synthesis. But synthesis would be a train wreck, so what's it going to be? Double displacement. So guys, you're going to come over here and you're going to put DD for double displacement. Now guys, classic double displacement, right? Watch me. The positive aluminum is going to hook up with the negative phosphate. But if aluminum's +3 and phosphate's -3, how many of each do we need? Just one. So one of our products is AlPO4. And yes, that spells Alpo, which is crazy dog food. And then guys, our other product, we've got positive calcium, double displacement, right? Positive calcium +2, hooking up with negative sulfate -2. How many of each do we need if they're plus and -2? Just one. So our other product is Ca, sorry this is kind of smushed, but CaSO4. Now guys, the last thing we need to do is balance this. We've got 2 aluminums, 1 aluminum, so we need a 2. Then we've got 3 SO4s, and we've got 1 SO4, so we need a 3. And then guys, this is where the magic happens. How many calciums? 3. How many calciums? 3. How many PO4s? Thanks to Mila, there's 2. And PO4s, we're done. That's it. So guys, with that said, please write these down before you leave. As I told you before, you do not know enough chemistry to predict the products of decomposition reactions. We're not going to do this.
Good morning, Tigers. Please stand for the pledge of allegiance.
So guys, number 3 is a decomposition reaction. You can just write DEC right now in the line. And the products of that decomposition are table salt and oxygen. By the way, don't forget oxygen's diatomic. Then, guys, number 6, again a decomposition reaction. The products are water and sulfur dioxide. Then, number 10, also decomposition, and the products are copper, metal, water, and oxygen. So on 3, 6, and 10, you can just put DEC on the line because they're all decompositions, and you will never be asked to predict the products. Now, in addition to that, there's one more I want to work with you on. Number 12 is a single displacement reaction. And then, guys, Josh, if you look at this closely, you'll notice that I mentioned that idea of treating water as H and OH. It makes it balance so much more easily. So, guys, that's it. My advice to you would be this: discipline yourself. Do not do this homework next Monday. You will remember none of this. Do this homework before the weekend is out so you remember it. Guys, we will grade this on Monday, Tuesday, and we will go to lab on Tuesday. Please remember that remediation begins immediately after spring break. You know what to do. And guys, I know that a couple of you are going to come take the test next Monday. That's fine. Does anybody else need to make test arrangements with me that haven't already? Beauty. Guys, have a